Hello, everybody. Welcome back to the AG seminar. So today we are going to be covering the universal property of tensors, and then we will be talking about fibered products, pullback diagrams, and leading into the base change diagram of pain and suffering, which we will take on in its entirety next time.
That's the official name, right?
No, but I mean it should be. Yeah. Yeah, no, it's a rough exercise. It took 2 hours the last time I did it, so I'm hoping that I have it down this time. Anyway, so okay. As a definition, we're going to define the tensor product over an object A as a map from Cartesian products of A modules to A modules, sending Mn to the tensor product through A of M and N. Now, you might be thinking, wow, that's a very helpful thing. That really tells us what this computation looks like. It doesn't. So the whole idea, and I want to give this as a preface because I'm still not entirely convinced that I know tensors very well. And I've met a lot of people who use tensors, like engineers and stuff, who say that they never really get a good foundation in tensors. And so I'm kind of trying to figure out the intuition as like something that we can attach beyond what we're going to attach it to in category theory. In category theory, the nice thing that happens is we have the Freyd-Mitchell embedding theorem, which says that we can construct any diagram with A modules, and that universal properties that hold for A modules hold for everything else that's in an abelian category, and maybe even an additive category. Tensors perform similarly. Tensors give us universal properties that we can factor through, and that kind of guarantee that things exist in nice categories. Computationally, though, it gets hairy. So what happens when we send a pair of like M in M and little n in N? What happens when we get the tensor product of like the small elements of the objects? Well, I have some examples prepped, but I'm just going to quickly list some properties that we're going to use that are fruitful for computing things. So if we have M1 and M2 tensored on the right with n, then this is equal to bilinear distributivity. But we also have this thing on the left, which is the same thing. I'm suddenly realizing that this is written a slightly different way. This is actually not correct. Let me take an orange thing and cross through it. And there's a reason why this is not correct. And it's a very important thing structurally. So you'll note that n goes on the right and n is in the right here. What I really mean is that it is right distributive for n and left distributive for n. So M tensored with N1 plus N2 looks like this. Okay. So with that in mind, we also have this property of scalars that A times a tensor product as a scalar is equal to AM tensored with N but is also equal to M tensor product with AN. So putting this all together, what we have is we have right distribution of N but then we also have left distribution of M.
A is not necessarily a field element, right?
No, A is, so, and I will clarify that Mi is in M, Ni is in N, and A is in the ring which supports the module.
Right,
Yeah. And then on top of this, we have bilinear scalars. Okay. There's a terrible way to form the tensor product of two A modules that involves quotienting. And I could present that first. That's certainly what happens in the textbook. I don't think that's a good idea. And so what I'm going to do is I'm going to give an example that, and I'm going to state some theorems, then give the example because it will just make life easier. And then we can kind of motivate the rest of the tensor stuff that we need to know. Okay, so theorem says that Z mod MZ or Z mod M tensored with Z mod NZ is isomorphic to Z mod the GCD of M and N Z. And this is kind of our first hint at the structure that tensor products obey. So when we go to compute things practically, what we are preserving in the tensor product is the shared support characteristic-wise of the underlying A module going on. And so this shows up in terms of the GCD. We're looking at shared support. So a lemma that we will use in our first example here is that the same setup above is also isomorphic to Z mod NZ mod M Z mod NZ. And I think this expression is a little bit misleading. It may seem like this is going to come out to be maybe semi-trivial, but it ends up leading to this above theorem. And so our example for this, or our first example for this, is going to be that Z mod 10 tensored with Z mod 12 is isomorphic to Z2. Now, by the theorem, we can say, okay, great, that works. But there's kind of the thing that makes the theorem work is more interesting. And so instead of proving it first, I think it's more helpful to give this example first. So consider just this part. So in this case, in context of the lemma, n we can say is the second thing is 12, and m is 10. So really, we know what Z mod NZ looks like, right? It's Z mod 12. But then we should be looking at M, the subgroup generated by M, in Z mod NZ. right? So the question is, the subgroup generated by 10 of Z12 is really the same thing as the subgroup generated by -2. Well, it's not too hard to see that if we take additive inverses, additive inverses, additive inverses, we're really looking at the subgroup that's generated by 2. We know that this has 6 elements in it, right? And so we can see fairly quickly that the order of this cyclic subgroup is 6. Well, we already know what the order of Z mod 12 is. And since there is only one group of order 12 divided by 6, we know that Z mod 10 tensored with Z mod 12 must be Z mod 2. So this is kind of using the lemma to construct the result that the theorem would give us a lot faster. But if you wanted to compute it by hand, this would be a fast way to do it. Any questions so far?
I was going to say, this just looks like easy group theory.
I mean, yeah, on some level it is. The kind of weird thing is what happens when we start looking at categorical properties of tensors. And we will get there. So I really like to try and give trivial examples, interesting examples, and horrible examples that make you not want to go too much further in a topic. And so I've kind of been struggling to find interesting examples. There's a lot of trivial examples. There's a lot of horrible examples. There are very few interesting examples. One of my friends actually gave me a really great idea, though, which is to just add 1. And so I'm going to go ahead and do that now. And this is going to kind of underlie most of the structure of what tensors do. So I made the comment up here about shared support structure is what the tensor product preserves. This is going to give us like kind of a visceral thing to see that. So consider Z mod 2 tensored with Z. So what we want to do is say that if we have 3 in Z tensored with 1 in Z mod 2 plus 1 in Z mod 2 tensored on the right with, I believe I said 2. Yeah, 2. In Z, we want to do a few things. So we want to use left and right distributivity. I can never pronounce that word, distribution. We're going to say that. It's not grammatically correct. I don't even know if the word I was trying to say is grammatically correct. Whatever. It's a math class. You're not here for my grammar. Using distribution properties, we get that 3 tensored with 1 tensored with 2 plus 3 tensored with 1 tensored with 2 is a thing. Rather, this is 2 times 3 tensored with 1 tensored with 2. But what do we also know about this inner sum here? Well, we know that this goes immediately to 0 because it's living in Z mod 2. So it doesn't matter, what order we apply things in. We have associativity. It should be the same thing. So we know that this is actually 0. Okay, well, in either of our A modules here, 2 is not 0, but 3 tensored with 1 tensored with 2 must be, because it's an integral domain. So what we're looking at is that the structure of Z2 mod Z really only preserves sums under addition, or rather its characteristic is limited by the shared support of the characteristic of the two A modules. And so this is kind of best said in two different ways. So one is that tensoring kills the torsion, which becomes invertible in the other factor. So left, like tensoring something on the right, kills the torsion that becomes invertible in the right-hand side. So all of the extra stuff that's floating around after 2 in Z that becomes invertible by characteristic class 2 gets thrown away. I don't think that that's a very clear way to say this. That's why there's a second line to this. Basically, tensoring kills the torsion that the other module can't see. So this right-hand side can't see the finite presentation of 2. So what do we kill off? We kill off everything that it can't see. Right? So we just reduce this to Z2. So this is going to lead me to a larger claim. I'm going to erase this if that's okay with you. So as a general theorem, Z mod NZ tensor with Z is just isomorphic to Z mod NZ. And that stands to reason. What are some other interesting things going on? Well, Z tensored with A is just isomorphic to A by the map that sends this over to the right-hand side. So we get we get Z many copies of A, but really this just looks like a bundle under A because we have no torsion on the left-hand side. Okay, I'll maybe mark this as second bullet, and this is a hidden first bullet.
So this is like direct product, but for modules. Kind of, maybe.
No.
No, not at all.
They share notation.
Okay.
They share notation, but that's it, right? Direct product usually means Cartesian product.
Okay.
Yeah. That's a very good question because I did not clarify that the notation didn't mean direct product. Yeah. Okay, another interesting example. I kind of can't, I don't know whether or not this belongs in the trivial or the interesting group. I'm going to put it in interesting because I have fewer of those. Z mod NZ tensored with Q is by our theorem going to be Z or is going to be Q mod NZ mod Q mod NQ is just going to be what it is. Sorry for the confusion. By lemma, this is Q mod NQ, which is trivial. This is Q mod Q. So we get the trivial ring. So all of these are kind of like interesting computational properties of tensors. They're things that we can compute that are down to earth. They make us feel like we know what's going on. I want to suspend this illusion. A lot of tensors are very confusing and implicitly categorical. And so there is something of a universal property of tensors. Which is that all bilinear maps factor through tensor products. Well, what do I mean when I say bilinear map? You know the dot product?
Yeah, I got bilinearity.
Yeah. Dot product factors through tensor products categorically.
Show me.
Exactly. So, this is kind of one of the weird results from today.
Is this a capital M or a lowercase m?
Capital. So if M and N are both A modules,
Okay.
then
I'm just asking because that is not a capital
N?
M.
Oh, yeah. No, I just had bad handwriting. So this is a capital M, right? What we're looking at is we're saying that if we have some bilinear form that sends it to this inner product, wherever this lives, it's going to factor uniquely, actually uniquely up to unique isomorphism through the tensor product. So this is just kind of like the property that's sitting in the background all the time with tensor products. Okay, I have a few other theorems about tensor products, and then I think I have some stuff with fibered products that I want to talk about. Because they end up tying together with fibered coproducts. Okay, so two theorems about kind of tensor products of rings and modules. Is that if M is an A module and we have a ring morphism from A to B, where A and B are both rings, of course. Then the tensor product through A of B with A is isomorphic to, we'll say C. No, I shouldn't use C because we were going to use that for something different. To L, which is a B module. Okay, so when we think about B modules, we are thinking vector spaces with coefficients from B. B is a ring, so we are looking at right distribution of A, and left distribution of B. And that is exactly kind of the implicit structure of a B module. Right? We have scalars that play nicely on the right. We have presentations of B on the left. Okay, a second theorem is that if A to C is a ring morphism, then the tensor product through A of B and C is a ring. Okay, so why does this work? Well, this works because we have well-defined addition that comes with the definition of the tensor product. So if we take B1 and B2 and C1 and C2 in this, then we can have B1 plus B2 and C1 plus C2 tensored together, and we can add things. Multiplication is the weird part. So I'm just going to say plus works. Multiplication is defined in kind of a weird way. I'm going to call multiplication star for now, just to be clear, and show when we're multiplying versus tensoring. So we're going to say that B1 tensored with C1 star B2 tensored with C2 is B1, B2, tensored with C1, C2 under their respective products. Okay, so why does this work? Well, this works because we're using all of the options for well-defined multiplication that we can get, and we're really looking at pointwise multiplication. And this gives us a natural ring structure. We don't need inverses in this way, so yeah, definitely a ring. There are definitely examples we can define where this is not an invertible thing. I don't have any off the top of my head, but I'm sure they exist. And then, yeah, it just kind of works. And then for distribution, that follows from the fact that addition is preserved and multiplication is pointwise. So I think these two are fairly reasonable theorems when you kind of talk them through. If you're just kind of staring at the notation, though, it definitely is like, what are we doing here? Okay. Two other main theorems about modules. So I'm going to call this one just you can localize by modules. So if we are given a multiplicative subset S of the ring A, and M is an A module, then S inverse A tensored through A with the A module M is isomorphic to S inverse M. So what are we doing? We're localizing the A module with a multiplicative subset of A. Well, why does this work? A is kind of already in the equivalence class of what works on the left with modules, right? Or rather with A modules. But the S inverse is not necessarily defined in a way that's cohesive unless A is a commutative ring where the group of units is the whole ring. And so the only case in which this is trivial is if S is A or if all of A is a group of units. Right?
So real quick.
Yes?
This feels like very familiar to that property, like the kind of like deletion property you mentioned before, where like we're deleting the information that the right side can't see.
Pretty much, yeah.
Side, right? Okay.
Yeah, like it's almost an equivalence operation of like if you have a polynomial with real valued coefficients and I multiply in something that's real valued on the left, it stays real valued. It has a different value in the polynomial ring, but it stays real valued. Okay. Any other questions on that?
No, I'm good.
Okay. Then theorem. So M, with all of the usual setups, sorry about that. So if M and N are A modules for all I, then tensor products commute with direct sums. This one is it's kind of a pain. Also, it's not equal. It's isomorphic. This one's kind of a pain to prove. It's mostly just a set theory thing.
This one just makes sense.
Yeah. It works the same way that it's just piecewise, right? Direct sums are well behaved in any like A module category sense. And then tensor products respect kind of the behavior of direct sums. So feel free to work this one out on your own if you're feeling kind of lost with tensors, but otherwise I think you can, or I think we can get away with letting this one slip as an exercise to the reader. Okay, so we have a decent amount of time left, more than I was expecting. So I'm going to introduce something that I introduced in lecture 0 very briefly, which is the fibered product. And we're going to show that a specific tensor is the fibered coproduct. Then I'm going to introduce the base change diagram of pain and suffering. Okay, so this is the fibered product. So this is a diagram other way. Okay, so this is the universal property of fibered products. What does this mean? Well, I'm going to make a definition. I'm going to say that the fibered product through Z of x and y is the set of stuff in whatever category that agrees in Z through alpha and beta. More specifically, in the category of sets, the fibered product through Z of x and y is the set of pairs in the product such that alpha of x is beta of y. And this is the transliteration of what I said in orange up here. So this is a very, very powerful property. This notion of agreement by some kind of map into Z gives us the ability to pull back from Z. Right? We're pulling back things that agree in Z through these maps. So affectionately, the fibered product through Z of x and y is called the pullback of Z. This can also, so this specific square here can sometimes be called a Cartesian square, a fibered square, a pullback diagram, a fibered diagram. There's like a whole paragraph in Vikielon. Like you can choose your religion with this and nobody will care. But when you see those words, like they mean the same thing. So the idea of W here is we're just saying that if W goes into X or W goes into Y, then it factors uniquely through the fibered product of stuff that agrees with Y going into Z. Do I need to say that twice?
Yeah.
Okay. When we're talking about W, we're saying that anything that we send to X that goes into Z through alpha has to factor through going into the fibered product of things that agree from Z in X and Y down into X into Z. Because there's shared properties on either sides of this. So as long as it's going to X and to Y, we end up getting the stuff that pulls back nicely, and then it happens uniquely. Okay. I actually feel pretty happy with that explanation.
The uniquely has to be shown.
Huh?
Right? The uniqueness has to be shown. Is it part of the definition that it's unique?
Yeah. 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 So
okay, so the fibered product is that.
Yeah, so it is the fibered product.
Okay, I got
Yeah, no, that is actually a very good point, and I'm glad you said that. So this is the fibered product. And the idea is that if you had a different morphism going into the fibered product, it is not structurally different than any morphism that you're going to have that is full. So as long as you have a full morphism into the fibered product, it's going to be full one way or another, and then you can have a morphism of morphisms, better known as a functor in the category of these two objects. That's terrible, though. You don't need that. Just take my word for it. They're uniquely isomorphic. Yeah, so then the fibered coproduct is, from a tensor point of view, the thing that we are more interested in. So in general, actually always, whenever you see the word co in front of something that we've talked about in the context of category theory, it just means take this diagram, flip all the arrows around, and figure out what makes sense here. So I'm going to define something very similar. There's not really a notation for it, so I'm going to invent some because it's easier than writing a whole lot. So I'm going to call this P, and it's going to be X fibered product Y co. There may be an actual notation for it. I haven't encountered it. I am not a category theorist. So yeah, just know that this means, the co-fibered product. So co-fibered product. Okay, so we switched the arrows. What does that mean? I'm going to claim that the co-fibered product is the collection of pairs that agree going backwards. It is the collection of things, if we're calling this alpha prime, this beta prime. It is the collection, and I have to be really careful about this, so maybe check me on this definition later. But I'm going to say that P is the set of Z and Z such that if we have alpha and we have beta, that, and I'm going to rename this from alpha prime, I'm going to call this theta and delta. Z and Z such that theta of alpha of Z is equal to delta of beta of Z.
Where alpha and beta in the co-fibered product are
not the same alpha.
related, not even just the same, but not necessarily related in any way.
Yes, not related in any way. So I'm going to add prime on there.
Okay.
Sorry, that's like a shaky definition. I don't like shaky definitions. Now there's an interesting tensor product that I have to find real fast. I'm going to claim that in our previous example, the tensor product through A of B with C is a fibered coproduct through A of B and C. There is a few things that I want to cover, so if we have time at the end, I will show this. Otherwise, it's probably worth seeing on your own. Any questions so far?
None that wouldn't set us back like 3 weeks. So just
Well, that's not good.
keep going as we're going. No, I'm just shaking on categories. But
Okay, okay. I guess just ask afterwards then.
like conceptually, I'm
Okay,
conceptually.
okay. Okay, so we're going to define a few things, state a few theorems, hopefully prove one of them, and then introduce the base change diagram. Okay. So, okay, so this is called the diagonal morphism. Delta pi from x to the fibered product through y of x with itself. What does this look like as a diagram? We have a map into y, and we have this map pi from x into y. Then we have a unique factorization through the diagonal morphism. This is used, I'm not really sure where else than the base change diagram. I certainly have not encountered it anywhere else. There's nothing particularly special about this other than the fact that it's kind of weird. And it looks like having kind of a diamond of x's. And then if we have some other morphism from x into y, then we have the things that agree in y. So if you can construct two different morphisms, this has the potential to be something interesting. Otherwise, if y is such that any x into it has to be automorphic, then this is just the product of x with itself. So seems fairly reasonable. So kind of related to that idea of when do things reduce down to be kind of trivial. If z in ob C is final, meaning that it has an arrow from every other object in the category, then the fibered product through z is actually just the product of x and y. So if we have an arrow from every other object to z, then the fibered product through z is just the product of x and y, because everything will factor uniquely through the product.
No, because it has to.
It like literally just has to. Okay, there's another one that for the sake of time, so when I originally worked through this book, I did this in 2-hour sessions, and I think that worked a lot better for being able to work through every single exercise. So it's somewhat reliant on people watching this to work through the exercises that I don't do on their own. Naturally, those 2-hour sessions are on my other YouTube channel, so feel free to go there and look at my solution for it. But I'm going to state this, and it's just going to kind of be like oh, okay, that's nice, we can chain this together. So if we have x and y and z and we have W and I. And then we have the fiber product here. Here's then I'm going to make a claim that the fiber product of through z of x and y is inherited as the fibered product of w and y through I, i.e. Cartesian squares stack and are still Cartesian. This is a useful exercise. You plop something in, you diagram chase it down, you show that it maps back through alpha and beta, or alpha and beta respectively. And since this first diagram commutes, it kind of helps to call this fiber product something else and say we drop something in here, we drop it down, we pull it back. It ends up in the same place as if we take it from its preimage in Z and pull it back. It's weird. It's diagram chasing. It takes longer than would be hoped, but it does end up making sense. I do recommend doing this exercise specifically. It'll just help you get a feel for category theory, diagram chasing stuff if you've never done it before. We're also going to do the snake lemma in, I think, like 2 weeks. Snake lemma is a big one. We'll probably do that in 431 as well. Okay. So this leads me to setting up the base change diagram. And at first, this is going to seem innocuous. It's going to seem like, oh, that's like cute. But there's a reason I'm erasing the entire board. And so I'm going to hopefully, I think I have time, draw out most of the diagram for the base change diagram in the next 7 minutes, and then next time we will prove it by diagram chasing. Okay, so I'm going to write it small over here, x1 fibered product through y with x2 goes over to x1 fibered product through z, x2 goes down to the diagonal morphism through z of y with itself, with y there is Cartesian. Now, to somebody who has not seen the definition of a fibered product, this looks like a fairly simple exercise. Even if you've seen the definition of a fibered product, you might be thinking, well, all we have to do is we have to draw out the square for each of these things. And then we have to put something in this first spot and chase it down this way, and then put something in this slot and chase it down this way, and then show that those are the same thing. It turns out to be a long process that we will do next time. But let's go ahead and start. So if we have the fibered product through y of x1 and x2, well, we can start by saying this goes to x2, this goes to x1. These things factor into y. We also have w that goes down like so. Okay, this is the first of a few things. But we also have x1 and x2 going to z. This is where colors help give us a little bit of dimensional insight. So if we put z here, and we have x1 through z, x2, that's tragic. Then this is the second piece of this, and we should have a morphism that I will put in purple that goes down like this. And this is all well and fine so far, because this is half the battle. But then we also have a different morphism that goes from the fibered product through y into y. Okay, this is starting to get weird. But we also need to establish the diagonal morphism of y with itself through z. Well, what does that mean we need? It means we need a fourth color. So if we have the fiber product through z of y with itself, then it looks like this. Except we also have this morphism here that goes from the fibered product of x1 and x2 through z to the fibered product of y with itself through z. So what is our ultimate goal when we log on next time on Sunday? Well,
Suicide.
you're going to get us kicked off YouTube. Fun. That is what it's going to be. We're going to put something in W. We want to show that it uniquely factors through x1 and x2 through y as a fibered product. So we're going to let little w be in W. We're going to drop it down in here. We're going to pass it down first to x1, then to y, then to z. No, x1 fibered product to x1 to y to the diagonal morphism. This is kind of the end target. Then we're going to drop straight down to x1, straight into y, straight into diagonal product. But then we also need to go into this fibered product, straight in to the diagonal morphism. But then we also need to go the other way. This is combinatorial hell, I think. So yeah, next time we will pick up again with the base change diagram of pain and suffering. I hope you enjoyed today's lecture on tensor products and fibered products and co-fibered products. Yeah.